of this area, and also in a bigger picture, the whole state of Maryland, and kind of hone in on Garrett County and go into a little bit more detail about that. And also talk about a few subjects that are of interest specifically out here, Marcellus Shale and why my well doesn't have any water in it, that kind of thing. So when I first moved to Maryland, which was back in the late 80s, if I'd thought about Maryland at all, I thought that it was kind of like rolling hills and suburbs, and yeah, the Chesapeake Bay is cool and all that kind of stuff, but it didn't really strike me as a really interesting place geologically, mostly because I didn't know that much about it. And we've all heard this phrase, America in miniature, that describes Maryland, and that is largely because we have so many varied geologic and topographic terrains here, in addition to other reasons. And now that I've lived here for almost 35 years, I've come to realize that there's probably more interesting landforms and geology and things like that in as short a space as any state has in the US, so it's pretty cool. And the reason it has all these different terrains is because of the geological structures underneath us. So I want to kind of look at the big picture first. And this is just some sort of satellite photo that kind of shows the whole range of the Appalachians. Just to put it in perspective, let's see. You are here. Okay, you can see that the Appalachians aren't just here. They go all the way up to Newfoundland and all the way down to central Alabama. So it's a pretty big range, and we're kind of right smack in the middle of it, okay? So we have to think about two kind of big concepts when we talk about the evolution of Maryland. And one is time, and we want to try to get our heads around just how much time has gone by since the Earth formed, and where is Maryland in that whole pile of things. This is a really god-awful thing to show you folks, but it's a gory detailed timeline of various geologic events. And it's got all these different periods divided up on it. And up at the top, it's got a more expanded scale, and over here, even more expanded, because the younger the rocks, the more we know about them. We don't have to know all this stuff. I just put it up there to show that there's been a lot of work done on the various ages of geologic time here. When I was in 6th grade, we had a science class that we were sort of acting up in, and as punishment, our teacher made us write out this geological chart 5 times. It's amazing I went into geology at all after that experience. One way we can get our heads around how much time has gone by, and there's a couple of different ways to do this. One way I like to do it is if you take all of the Earth's time, 4.6 billion years, and you pack it into like 1 year, and then you look within that year to see where various events occurred, that kind of gives us a better sense of how much time's gone by and what happened when and so forth. So if we have January 1st as our new year, so to speak, we didn't see really anything in the way of life until almost 4 months later. And that was very simple life, single cellular life. And there's not a whole lot of record of that. And there's a lot of argument about when exactly the first life appeared, but it's somewhere around there. And then nothing really happened in terms of evolution of life for a long time. So now we're all the way up to November. And this is when we first see a very large explosion, or radiation, as they say, of different life forms. And this was all in the ocean. Okay, it wasn't until late November that we had life appearing on land. Now finally, we're talking about Garrett County here. This is the age of the Garrett County rocks. So late November, early December. So they seem old to us, and they are old. They're a couple of 100 million years old, but in the terms of the age of the Earth, not so much. And the dinosaurs came sometime after that. They're pretty late in the year too, aren't they? The most recent ice ages, the last day of the year. And humans, more or less in their current form, showed up about 100,000 years ago, so we're talking about 20 minutes before midnight on New Year's Eve. And if you really want to feel insignificant, a human lifespan is less than a second long. So how do you feel now? Significant? I had a professor who had made the observation that geologists as a group tend to drink more than most people. And his theory was that we're one of the few groups that have a really good sense of time and how little your time matters in the grand scheme of things. So if you realize that, you might as well enjoy yourself while you're here. So that's one of the concepts we need to understand something about. And the other one is this concept of plate tectonics. Sometimes it's called continental drift. And this is the idea that the surface of the Earth is kind of like an eggshell. It's not very thick, and it's actually able to move. And this is something that's been thought about for hundreds of years, but it's only been understood in terms of the mechanism for maybe the last 100 years, or even less than that. And the idea here is that the plates, and there's about maybe 7 major plates, and 8 minor plates on the surface of the Earth, and they're all sort of moving around as a result of convection cells in the mantle. This part of the Earth's interior is sort of a plasticky consistency, okay? And it develops currents from the heat, and the heat is generated by radioactive decay of elements in the core. So when you get these circular motions here, you can understand how it starts shoving these little pieces of the eggshell in different directions. Some of them go apart, some of them come back together again, some of them go this way, and all combinations of those things. And we'll find out that this is something that helps explain why we see what we do in Maryland. Okay, so back to the big picture. Maryland is, here we go. This is a nice colorful map. It's a geologic map of the state of Maryland. It's a very generalized map. And what this shows is, or the way they make geologic maps is, it's as though you go out on the surface of the Earth and you take a bulldozer, you scrape everything off the top, all the soil, all the buildings, everything, and then you just have rock exposed, and then you paint each kind of rock a different color. Then you go up in space and take a picture of it. It's a very generalized picture. Every one of the counties here has much more detailed geologic maps that we've done in conjunction with the USGS. But you can just look at this thing and you can see there's a lot going on, or there has been a lot going on geologically. So I want to look at each of these areas, and we'll eventually wind our way up in Garrett County. So we've got what we call physiographic provinces, ranging from the coastal plain. Central Maryland is the Piedmont, and the Blue Ridge, Ridge and Valley. The Appalachian Plateau is out where we are. These all have distinct characteristics. So I think the best way to sort of get an idea of what we're looking at here is to take a slice of Maryland. So this is a cross-section that just goes from western Maryland out across the coastal plain here. And you can see that there's been a lot going on here over geologic time. Otherwise, everything would just be one color, or at least concordant layers. So if we start in the east with the coastal plain, I think that's, yes, here we go. So this is a block diagram that we're kind of looking northeast from space somewhere, and just for reference, here's Washington, D.C., here's Baltimore, Chesapeake Bay is here. And this, what we call the fall line, is more or less where I-95 is, and it separates the coastal plain from the Piedmont. And all the materials that underlie the land here are unconsolidated sediments. They're relatively young sediments geologically. They occur in very distinct layers. They alternate between sand layers, gravel layers, clay, silt. We've mapped them all out. We know where they are. They're very productive aquifers, which I'll talk about later on. And you could theoretically go down to Ocean City with a shovel and just start digging, and you wouldn't hit competent, hard bedrock until you got to about 1.5 miles deep. It's a very thick pile of unconsolidated material. So coming west, we get to the Piedmont and the Blue Ridge, and in contrast with the coastal plain, which has some of the youngest sediments, the Piedmont has the oldest rock of all, more than 1 billion years old in some cases. It's all igneous and metamorphic rock. Igneous rocks are just the ones that form from molten magma, solidify underground, usually. And metamorphic rocks are pre-existing rocks that have been compressed, squeezed, heated up, changed into some other kind of rock. And you can see by these little squiggles here that there's been some pretty severe crunching going on, which we'll talk about in a little bit. Interesting, some of the building stones that they use in Washington and in Baltimore come from this area. The Cockeysville marble in North Baltimore County supplies a lot of the building stone for the buildings in the nation's capital, the Washington Monument, the Lincoln Memorial, and a lot of other buildings. It also provides the stone for the famous Baltimore white steps that people are always out there scrubbing and getting real clean so you can sit on them and talk to your neighbors. So that's the Piedmont and Blue Ridge area. And moving out west, now we're getting to the best part of Maryland, of course. This is the Valley and Ridge and the Appalachian Plateau. And what I want you to see here is, so we're right around here, these are sedimentary rocks, and these lines here are faults that have been generated by continental collisions. And you can see that the farther west you go, there's a little bit less contortion to the rocks. They're a little more sort of undulating, not so much faulted and highly contorted. So these are the rocks that make up where we are. This is just a shot of the Hagerstown Valley, looking from, I think this is Annapolis Rocks. Big wide valley in marble, limestone out there. All right, so Sidling Hill Road Cut, you all been through there? It's pretty impressive. I think when I first came through that's when I realized something special was going on in Maryland. Just a beautiful road cut. And it's got these folds that we have to have a 50-cent word for it in geology. Anything that's folded down like this we call a syncline. If it goes the other way, it's an anticline. So let's take a closer look at these kind of structures in western Maryland. So this is just a block diagram, a generalized diagram of what we have going on here. Now, Sidling Hill could have been this hill here. We've got this little bit of a syncline here. But in general, what you can see is the sort of undulating geologic structure, alternating sandstones, some limestones, shales, and so forth. We have our synclines and our anticlines. The thing I want you to notice here is it would be reasonable to assume that where you have these synclines going down, that would be where the topographic lows are, okay? Just kind of seems like it would make sense. And we do see that in some places like here, but we don't see that everywhere. You can see here we've got this anticline going up, but we've got this valley in the middle of it. We've got this syncline here, there's a valley there, and there's another anticline here, and there's a valley there. So why does that happen? Well, there's a couple of reasons why that can happen. One is that when you have this bending of the rock, if you can imagine continents are colliding and this thing is bending, there's a bunch of fractures that develop in the top of those structures. And where you have fractures, you have more water getting in there and snow melting and ice and all this kind of stuff. And it's more easily eroded through the freeze-thaw cycles and carried off by whatever stream is in the area. So that's one reason you can get the valleys formed in the structural highs. One of the things we see a lot in Garrett County is in between the lows here and the highs here, we have this ridge forming, okay? We see it here, we see it here, we see it here. And this is because those particular rock layers that are sticking up on the ridge tops are much more resistant than the other layers of rock. The shales tend to erode very easily. The sandstones are pretty difficult to erode. So if you've been up on Dan's Mountain or you've been up on Meadow Mountain Trail or High Rock, you'll see these rocks that are, and I'll talk about the particular kind of rock, they're all tilting a little bit. All right, so let's think about how Garrett County got to look the way it does, okay? The geologists who are familiar with all the different strata out in this area and in Pennsylvania and West Virginia and other areas have identified 3 separate packages, for lack of a better term, of sedimentary rock, okay? And I'm just going to go down this in oldest to youngest chronological order. First of all, if we look at this cartoon on the right, what we had happening back when the first rocks started to form, or at least the first sediments were deposited that became the first rocks, we had a bunch of continental fragments that were migrating toward Maryland. And this oceanic crust, when it got shoved this way and connected with North American continent, this crust is fairly dense, denser than the continent. So it starts going underneath. We call it subducting. Got to have a 50-cent word for it. And when that happens, you get mountains forming, okay? So we had all these mountains being uplifted as a result of these continents coming over, parts of continents coming over from the east. And then the mountains do what mountains do. They erode. And so all that sediment over tens of millions of years wound up draining to the west. And we had this shallow inland sea off to our west, and this is where the sediments wound up after they got eroded off the mountains here. A little counterintuitive. We're used to thinking of the ocean on the east side, but here it's the other way around. So that was the first groups of rock. And actually those rocks, they're underneath us here, but they don't outcrop at the surface here. They're buried very deep. And then we had the same sort of thing happening again about 50 million years later. We had the African continent over here starting to encroach on the North American continent, and again it started subducting this crustal material under the North American continent. Once again, it's causing all these mountains to be lifted up and subsequent erosion, filling in what we call the Catskill Wedge. Catskill Mountains in New York, that's what these things are. And we have a number of rocks here from that wedge that are exposed at the surface, Devonian age rocks. So that happened until the mountains got eroded down again. It takes a lot of time to do that stuff, but over time it happens. And then last but not least, finally the African continent wound up slamming into the North American continent. All this crustal material, this ocean crust, had been shoved underneath. The continent moved all the way over, and now we have 2 continents crashing together, and the rocks are of a similar density, and when that happens, that forms the highest mountain ranges that you can find, because one isn't getting shoved down under the other. They're like fighting each other. And that's what developed the Appalachian Mountains. So we have this very tall mountain range now, And what does a tall mountain range do? It starts eroding. So that provided the source of the last bunch of sediments out here from the erosion of those mountains. And pretty much since that time, there hasn't been any other collisions around here or any other deposition of sediment. So I thought I'd mention just a couple of the kinds of rocks that you might have seen around here or might be familiar with. Excuse me, tail end of a cold here. One of the rock units that's important as an economic source is the Oriskany sand, which is a Devonian, very porous sandstone, and it forms reservoirs, gas reservoirs in the Mountain Lake Park gas field and also in the Accident Dome. And also it's produced a lot down in West Virginia and some other areas too. We see a lot of fossils in it. It's a very clear look, or not clear, but white looking sand. A lot of the porosity that causes the gas to be there is due to fractures in the rock. I'll talk more about that in a minute. Also, we've all heard about the Marcellus Shale. This is a very organic rich shale that we find at depth here. And this is an outcrop not in Garrett County. It doesn't outcrop in Garrett County, but in Pennsylvania. And one of the largest outcrops in the county is this unit called the Hampshire Formation, which is this very red sandstone, sand shale alternating unit. And if you're lucky, you can find chunks of this rock that have these beautiful ripple marks in them. It looks just like something that you find in a stream with unconsolidated stuff getting deposited, only it's 250 million years old. It's very old. It's really beautiful. If you're trying to put in a garden, it's a terrible rock to have under your house because it's got nothing but rocks at the surface. I know this, unfortunately, from personal experience. Okay. A couple of other rocks that we have in the area. The Greenbrier limestone. This is not a very thick geological unit, but where it is, it can be very significant because it has some caves in it. Crabtree Cave, you may have heard of, down on just near Savage Reservoir. Number of other caves in the area. It's very permeable. Limestone will dissolve, and that's good and bad in a way. It's good if you're drilling a well and your well goes through a nice layer of limestone. It can produce a lot of water. The bad news is it can be very easily contaminated from something that's happening a long ways away. And it's often very difficult to determine where the contamination is coming from. And of course, we have a number of coal beds in the younger deposits, which I'll talk more about that. So what the coal beds tell us, and actually the limestone too, these indicate that when we look around to see where this stuff is forming in the world today, the limestone only forms near the equator, forms where it's relatively warm. There are some exceptions, but that's the bulk of it. And so from that, we infer that this area was tropical at some point, which is kind of cool to think about, especially in the winter. And coal, same kind of thing. It represents old swamps, like think the Okefenokee swamp, something like that, where very thick layers of vegetation have grown and died and been preserved and eventually turned into coal. And the last one I want to mention here is the Pottsville Formation. This is the one that I was mentioning forms the ridges. So if we just look at this cross-section, here's the shot of, this is high rock. Dan's Mountain, you can see there's a topographic high there. That's where the Pottsville Formation outcrops, and it kind of curves down and outcrops there at Backbone Mountain, again at Meadow Mountain, Negro Mountain, and so on and so forth. This is also where you get a lot of waterfalls forming, muddy falls, and let's see, here's Muddy Falls, and there's High Rock again, okay? And they don't call it the Pottsville in West Virginia, but it's my understanding that it's the same unit named something different that forms Blackwater Falls down in Tucker County. So I wanted to mention a couple things about energy resources here. Like I mentioned, there's 2 natural gas fields. Mountain Lake Park doesn't produce anymore. When it was first beginning to be produced, they drilled a whole bunch of wells in it. They drained it inefficiently, and they stopped production. And in the Accident Dome in the north part of the county, they drilled it a little bit more rationally, and eventually the depletion declined there too. And now it's used as a natural gas storage field. They bring gas in from other places in the United States. They pump it into the geologic formation because they know it can hold gas without leaking. And then they release it when they need it in the wintertime, and they send it to other parts of the country. So why do we see coal and why do we see natural gas collecting where we do? So again, this is our slide we've seen several times. The coal seams are in the youngest rocks that we see in the county, or in Pennsylvanian age rocks. And those rocks only occur, this is where those rocks are located, this green, green, green. And so if we look at where the coal is mined, that's where they are. So the coal used to be in this arch over here, but it all got eroded away, okay? Now for natural gas, the way natural gas and oil, for that matter, work, how they're generated and how they're stored, the sedimentary rocks contain a fair amount of organic material around here. And as they get buried deeper and deeper, they undergo a change with the increased temperature and the increased pressure. And eventually the heavier molecules, the heavier organic material gets broken down into lighter hydrocarbons. And what that stuff wants to do is it wants to migrate upward. You think of, oil and water in your salad dressing bottle or whatever. The oil's floating on the top. These rocks are permeable, okay? They have fractures in them, they have porosity in them, and where there's not organic material, there's water, and it's usually very, very saline water. That's why when you produce natural gas and oil, there's a lot of very briny water that's associated with it. But if you think of all this brine water and all this organic material being generated, that stuff starts to float upward in the rock. And it will float upward until it can't go any farther. And typically, at least around here, what that means is that if you've got hydrocarbons being generated around here, it's going to migrate up into one of these anticlines until there's a unit that it can't go through anymore, typically a shale that's got very impermeable material in it. And so typically we find the oil and gas deposited in these structures, and they're often associated with this faulting. Apparently that increases the permeability of the rock. So it's kind of interesting. We have this alternating coal here, natural gas, coal, natural gas, just based on the way the rocks work. All right, so Marcellus Shale has been in the news in the last 10 years, and I know that was a pretty heavily debated topic out here. There hasn't been any drilling into the Marcellus Shale due to I guess it was a moratorium or an executive order by the governor. And if you recall, the way the Marcellus Shale works as a gas producer, it's a very thin, relatively speaking, it's like 100 feet thick or less. It's a thin shale. It's got a lot of organic material in it, but it doesn't produce it very readily. And so when you're drilling into this, what you do is they drill down straight and then they kick the well out. They're actually able to drill horizontally for thousands of feet. It's really kind of mind-boggling how they do this. And then they inject high-pressure water and sand into the formation, and it fractures it. And that makes the gas flow much more easily. Well, if you're an oil company, what you want to do is you want to find a place where the Marcellus shale is the thickest and also where it has the highest degree of organic content. This is a map that shows the thickness of the Marcellus shale, and you can see, this goes up into New York and Pennsylvania and down into West Virginia. You can see that the thickest part, it's the red, and it's more in northeast Pennsylvania going down to southwest Pennsylvania. And we're kind of off to the side here. It's a lot thinner here, and that's one of the reasons I think it's unlikely the gas companies would have drilled here anyway. It's just not as optimal looking as it is in the areas where they have been drilling. But one of the things that came to light when we were doing some work on this, we had a couple of mappers from our office out doing quadrangle level geologic mapping in Garrett County. And what these folks do is they go out and just walk all over the hillsides and look at outcrops and try to figure out, first of all, what rock is there, where's the boundary between that and other rocks. And it's not always easy to do because there's all kinds of trees and forests and houses and stuff. You go out west, it's a lot easier to see rocks. But anyway, one of the things that they discovered when they were doing this mapping is they identified areas where it appears that there are faults that have come all the way up to the surface. And this is the only place, according to the fellow who identified this, he said it's the only place in the Appalachians that he's aware of where these faults come all the way to the surface. So what does that mean for a gas company? Well, what that means is that if that's there, and they're not sure exactly if it is or not, but there's some evidence to support that idea. What that means is your Marcellus shale, which normally is horizontal or at least continuous, all of a sudden it's offset by maybe 50 feet. And they're not very big faults. They're not like the San Andreas. So if you're a gas company, you don't want to drill along and all of a sudden you get to the end of this level and you drill across the fault and it ain't there. It's up there. So it makes it less attractive to drill, less economical in a case like that. Okay. I wanted to talk a little bit also about groundwater. This is the area that I was working the most in when I was at the Maryland Geological Survey. And groundwater is this kind of mysterious substance. I mean, most of what we know about it is by remote sensing or hit or miss wells or that sort of thing. And so this cartoon shows how groundwater works in different areas of Maryland. So in the coastal plain, I mentioned before that you've got unconsolidated sands and gravels, and there's all these pore spaces between them. Water can flow through it really well. Think like when you're down at the beach, like close to the edge of the water, and you dig a hole, and all of a sudden you see that seawater come seeping in. That's just groundwater flowing through unconsolidated sediments. These aquifers are very prolific. We had one well that they drilled down in the Salisbury area. They did it was a test well for a municipal field for Salisbury, and they did a pump test on it, and they pumped it at 3,000 gallons a minute. Imagine that. You fill up your swimming pool in about 5 minutes, So they're very productive aquifers, and they're very well documented. We developed a tool, actually, at MGS where you could take your mouse and click on anywhere in the coastal plain, and it would tell you exactly the elevation, subsea depth to every single aquifer and every single confining unit. and it would also have all these hydraulic properties, and it was helpful for making computer models of groundwater flow. Unfortunately, we don't have that out here. So in the Piedmont and the Appalachian Plateau groundwater situation, they're a little bit similar, different kinds of rocks, but the idea is that there really isn't very much intergranular porosity or permeability. Most of the flow that you have in the groundwater in those areas is in fractures. And the problem with that is that it's very hard, if not impossible, to tell ahead of time where you're going to encounter a fracture, because they're at all different angles. Some people have better luck than others at sort of reading the topography. Usually if you have little swales, they can be areas where fractures have developed, and you kind of think three-dimensionally, and you can maybe improve your odds of having a productive well. But it's very hard to do, and I think that in Baltimore County, I think they will approve wells, water wells for domestic purposes if they're only flowing 2 gallons a minute. So typically they drill very deep wells, and they might have a couple of fractures that are feeding water into them, and they use most of the well just as a storage tank, basically. So out here, well, let me first say, in the ridge and valley, like think the Hagerstown Valley, there's a wide expanse of limestone in the valley there, and that area has very permeable rock, okay? There's a bunch of caves there, water is flowing through there like streams, although it's hard to tell exactly where you're going to encounter one, but you can have a very good flowing well if you happen to hit a nice vug or something like that. Anyway, so out in the Appalachian Plateau, we have these fractures that are transmitting the water, and in addition to that, because it's sedimentary rock, we also have these bedding plains, and sometimes those will be very good transmitters of water, other times not so much. How do we high grade our well location? Well, it's pretty hard to do. There are places that they've had to drill 800 to 1,000 feet for a domestic well. I mean, that's a lot of money. And it varies spot to spot. Okay. So the other aspect of, I was just talking about this. So again, this is sedimentary rock, and these lines here are fractures that go between the aquifers. And let's see, what else? These areas, these horizontal areas, are bedding plains that can also transmit the water. And like I said, it's very hard to know how transmissive they're going to be. We also have some issues with water quality out here, and you guys probably know this better than I do. We have a lot of wells with high levels of iron and manganese, which fortunately it's an aesthetic consideration. It's not a health issue. We do have some places where we have higher concentrations of sodium and chloride. Typically, those are related to road salt, but not always. We do have a couple of places where there's evidence that there's deeper brines that have come up in the shallow subsurface for whatever reason. They're not very common, but most of the high levels of chloride are associated with proximity to roads that have been receiving road salt. You mentioned the iron and manganese. In the Hampshire Formation, that reddish rock formation that I talked about before, it turns out that about a quarter of the wells there have exceeded the drinking water standard for arsenic. So several years ago, the EPA, Environmental Protection Agency, lowered the drinking water standard for arsenic from 50 to 10 micrograms per liter. And we had a lot of wells that were in that range, so we went out and did a survey of more wells and tested them for arsenic. And it appears to be only wells in that geologic formation that have it. And arsenic is kind of a nasty substance. If you have a well that you're concerned about and you don't know if it's been tested for arsenic, you can call the health department and they will test it out. So the area that we're talking about is this area in here. You can see these red and yellow dots indicate the wells that have had drinking water exceedances for arsenic. And all these other areas, not so much. That was one of the things that I was trying to do for most of my career. We would go around the state and map out areas that had different contaminants, naturally occurring contaminants in the well water. So that's kind of a whirlwind tour of Garrett County geology and other things. And thanks for listening. I'd be happy to answer any questions that you might have. Anybody?
How do they know how old these rocks are?
Well, that's a good question. There's two ways that they date rocks. Igneous and metamorphic rocks, they can identify by looking at ratios of unstable isotopes in certain elements, uranium, thorium, there's a whole bunch of them, and they know the rate at which these isotopes decay. It's a very specific rate. And by measuring the ratio of one isotope to another, they can kind of count backwards and determine when it formed. Sedimentary rocks, it's a little bit harder to do, but one way they do it is they look for areas where igneous rocks have been intruded into sedimentary rocks, and if you can get a date on the igneous intrusion through isotopes or other means, then you can use that as a minimum date, or you know the sedimentary rocks are going to be older than that. So if you know those rocks' age, then you can kind of correlate those rocks with other rocks around the country, around the world. They can also do it to a certain degree by looking at minerals in sedimentary rocks, minerals that have cemented the sediment particles together. So, a couple of different approaches. Jeff?
Something near and dear to my heart is how does sulfur get into our well water? Maybe you can perhaps suggest that.
We haven't really looked at that too much, other than sulfate-reducing bacteria get in there somehow, and there's some sulfate in the rocks and in the water, and if you have those bacteria, they use that as their energy source, and the result is your water smells like rotten eggs, as you know only too well. Yeah?
There is a local legend that in the late 1800s, a hunter along Meadow Mountain found a block of silver and could never find this, he was kind of lost and he was never able to find the spot again. Do you think there's any validity that there could be silver deposits?
It's unlikely. There are places in Maryland where people have looked for gold and maybe silver also. Usually those deposits are associated with igneous and metamorphic rock, and what they usually are areas where there's been very hot hydrothermal waters that have been forced into the pre-existing igneous and metamorphic rock, and when it does that, it undergoes a chemical change that causes the metals to precipitate out. So they're in veins most of the time. I know people have gone panning for gold down in the Potomac River, and they find some of that, but I don't think they've found like the ore that's in the rock. What they find is what they call placer deposits. That gold gets eroded out and winds up in the sediments down here, and then they pan for it. I had not heard that.
One of those old clean stars.
Okay. I'll have to look for that, because there's all kinds of interesting stories about people finding, nuggets the size of footballs, and at least down in the hard rock part of the state. So, interesting. Anybody else? Yeah.
Can we talk about the eastern shore for a second?
Sure.
This 3,000 gallons a minute coming out of this well in Salt River, are they at all concerned about saltwater intrusion going into the layers to as well as go down the aquifers that they did?
In that area, they weren't because they were fairly far inland. But there has been a problem with that in other areas on the eastern shore, particularly Kent Island. When they built the Bay Bridge back in, was it the 50s sometime? So all of a sudden, it made it easy to commute from the eastern shore over to Annapolis or wherever. And people wanted houses on the waterfront property on the western shore of Kent Island. So they went over there and they plopped all the houses down, put the wells in. And it turned out, through a geologic anomaly, there was a connection, a hydraulic connection between the bay and the aquifer right at the shore there. And so they started, they developed the area, people started pumping water out of there, and all of a sudden this salt water migrated into the aquifer over 20 years or so. And we actually developed a computer model of that to show, just how fast it was going to intrude. And it was such a problem that they wound up putting that community on public water, and they had them plug in all their wells. Once you get salt water into a well, it's very hard to get it out.
Yeah,
So.
I lived in Florida for 28 years.
Oh, okay.
Company down there, and Miami has no groundwater that they use. It's all destroyed.
Yeah. Yeah, if you have too close a proximity to salt water and your wells, if they haven't looked at some models of how much to pump, it can be a real problem. It really can. We did some other computer models in the southern Maryland looking at not saltwater intrusion, but we wanted to know, the counties wanted to know how much can they pump without causing drawdown, the water level dropping in the up-dip part of the aquifer. And it turned out that with some of the plans they had projected growth in certain areas, and under certain pumping scenarios, the water table was going to get to a point where it was not, it was below where they needed to be, and so they were able to adjust their locations of the wells to avoid that. But, yeah. Yeah. Go ahead.
When I lived out west, I had a good friend in the ranch, and they had all kinds of fossils. And even when I was around, the part of Wyoming I was in, there were lots of fossils easily to find. I find that when I've been doing exploring in like Pennsylvania and West Virginia, we find like little seashell fossils and things like that. Why are there no dinosaurs in this part of the country versus?
Well, part of the dinosaurs in particular, it depends on the age of the rocks. And we just don't have that age rocks here. And out west, there was this huge inland seaway that supported that kind of life. And not only that, but when dinosaurs died, they were in an area that would preserve their remains. I mean, when you think about, it takes a certain combination of luck to have a fossil preserved. You have to have it in an area where it gets buried right away after death, and it has to be in an area or an environment where it doesn't decay once it's buried. And if you look around on the earth today, you see deer on the side of the road all the time. Well, those are going to be gone in about 5 days. You're looking at places like marshes where there's a lot of organic material that seals it off from the atmosphere. So I think not only were the dinosaurs, common out west, but it was just a more conducive environment to preserving them. There's also there's a formation out there called the Green River Formation in Wyoming that has all those wonderful fish fossils. It's just beautiful, and those are much older than, I mean, much younger than dinosaurs. Those are Eocene. But
I found some like fish or ocean fossils
Yeah.
up in like the little caverns area.
Huh, okay.
So there's some limestone
mm-hmm.
things over in Pennsylvania where I found some pretty interesting fossils that they're mainly sea related.
Mm-hmm. Mm-hmm. I've been in some caves in West Virginia where they had these things called crinoids or crinoid stems, which are basically like sea lily kind of things, and they're just sticking out of the roof of the cave. Just beautiful things.
Out west, my son would go hunting and he would come home with like pockets full of fossils and rocks, and he'd be like, "Take a look at this one."
Well, ask my wife. Our basement is full of boxes with all kinds of rocks from all over the country. Yeah.
Wondering back in their heyday, how tall they estimate the Appalachian Range to have been.
What I remember hearing, don't hold me to this, it could have been as tall as the Himalayas, 20, 30,000 feet. But I can't cite my source, so.
I've heard that also.
They were pretty tall. When you have two continental masses coming together with densities about the same, it really makes things grow. It's like the Himalayas today. You had the Indian plate crashing into I guess it's the Asian plate, and similar kinds of rocks, and makes for tall mountains. Yeah.
Does Maryland have any notable rock formations or deposits anywhere that make it unique?
Every rock is unique in Maryland. Well, it depends on what kind of unique you're talking about. We have rocks that are very good for certain industrial purposes. We have building stones that are just beautiful. I guess there are some minerals that are pretty somewhere. I don't know much about the mineral scene here in Maryland, but let me think. What's that?
Talk about chromium.
Oh, that's true. So in the Piedmont of Maryland, in sort of a big arc going from Baltimore up to Philadelphia, really, there's this deposit called serpentine. And it's distinguished by, when you're driving along or walking along, all of a sudden there's these areas where nothing grows on it because it's absent all the right minerals for things to grow in. And it turns out that it has a very high percentage of chromium. And for a while, back in the early 1800s, the Baltimore area was the largest producer and refiner of chromium in the world. And it was all from this little thin deposit that goes up through Baltimore County. And it was, you've heard of Allied Signal, they had a processing plant down in the Inner Harbor, which they used for years and years until I guess they had to clean it up because of the pollution. But it was a huge operation. But this deposit was not all that thick. It was maybe 6 or 8 feet thick. There's a state park there. You can go out and actually see some of the old pits. And they stopped mining it there when they found these immense deposits of chromium in China and in South Africa, things that were like 10 feet thick and went on for miles. They could just get in there with some heavy-duty machinery and mine it out. So, yeah, thank you for reminding me of that.
Last year, I went down to the quarry hockey field.
Mm.
If anybody wants to see it, I mean, it's still being quarried right now, and like you had get some of that marble, was used in the marble stuff, Washington Monument, the Capitol.
Yeah.
It is currently being mined, I mean, they still do it.
Yeah, it's a huge hole in the ground, too. I was teaching a class and you can barely see it from the highway. I think they did a really good job of disguising it. Mm-hmm. I was told by the consulting geologist there's one area It's like a tunnel. There's a big, big, huge pit, and there's this one, looks like a cave. And he said that that's one zone where they have ultra-pure calcite, and they only use it for specific purposes, like where you need a certain grade of calcium carbonate. But they use it for things like, the one that I remember is gum wrappers. They use it as that powder on gum wrappers because it keeps things from sticking. That's an important rock. Somebody else have? Yeah.
What's your favorite geological feature of Garrett County, and what was the most satisfying or enjoyable project you worked on during your time?
Okay. It's hard to pick in Garrett County. We've been to most of the high points like this one, and I just love that because you can see forever, and it's also really neat to see places like Muddy Falls and Swallow Falls. So that's pretty cool. As far as the most satisfying project that I ever worked on, this was actually interesting. Well, you can be the judge of that. We were doing a study of carcinogens in groundwater in Anne Arundel County. They had found, there was a cancer task force that they had discovered that the county cancer rate was higher than the state average and the national average. And so they didn't really know why that was. And so they started looking at different compartments of cancers, types of cancers. And mostly what they found was that it was mostly lifestyle related, tobacco use and so forth. But in the process of doing that, they realized that they didn't have any information on carcinogens in private well water. So, all the public supplies are tested for every regulated carcinogen. So they hired us to go and do this and look at different contaminants. And so we went out there and we tested about 50 wells, and all the numbers were sort of trickling back from the lab, and it all sort of was what we expected. But one of the things we tested for was 2 isotopes of radium. And naturally, this was the last stuff to come back from the lab. And when they came back from the lab, they were way above the drinking water standard for public supplies. And radium is a Class A carcinogen. It's one of the few carcinogens that we actually have really good, unfortunately, good data on human exposure. And most of this comes from this industry back in the early 1900s, where they were painting radium on these watch dials and all kinds of dials, and it was mostly young women who were employed here, and they had these little pots of paint that they would paint it, and you wanted a nice sharp tip on your brush, so they would lick it. And they were ingesting all this radium. And not too long after they were doing this, there was this very high level of head cancer, neck cancer. So this is something to worry about. And so we got this data, and we went out and did a whole bunch more testing. And it turned out that almost 50% of the wells in this one area of Anne Arundel County exceeded the radium standard. Fortunately, most of these houses had water softeners. The water is very acidic. pH was below 4 in this area, very acidic. So they typically would have a neutralizer on there. The neutralizer would put calcium into the water, which made it hard. So then they had a softener on there. Well, it turns out that calcium and radium are the same chemically in terms of reaction, and the water softener would pull out all the radium. So there really wasn't exposure to it, fortunately. But what we did is we took all this radium data and we took all the well depth data, and we were able to generate a map in this area to show how deep they had to go to get below the radium. The radium was only in the very shallowest part of the aquifer. So that was pretty satisfying to do. I felt like I was contributing something to the public health here. Yeah.
Speaking of that, I
I only know that there's not a problem, there's not a high level of radon in the groundwater. As far as, and the concern about the radon in the groundwater is that when it comes into the house and you're running your faucet or your shower, it volatilizes and then you breathe it in. So it's the same mechanism as if it's just seeping into the house from the soil. I'm not aware that it's a problem, but I really don't know. Health department would know something about that. All right, well, thanks. Thanks for listening.